Anatomy of a vector: initial point, terminal point, and magnitude. Welcome back, everyone. In our previous lesson, we established the fundamental definition of a vector, that it is a quantity characterized by both magnitude and direction. However, simply knowing that a vector has size and direction isn't enough when we start solving complex problems. To work with vectors effectively, both mathematically and geometrically, we need to look under the hood and understand the specific components that define a vector's structure. You can think of this as learning the anatomy of a vector. Just like studying the parts of a biological organism, we are going to break down exactly what makes up a vector, specifically focusing on its starting point, its ending point, and its overall length. 1. The initial and terminal points. If you look at the screen, you'll see that geometrically, we represent a vector as a directed line segment, which is really just a fancy way of saying an arrow. Because it's an arrow, it has two very distinct ends that we need to identify. First, let's talk about part A, the initial point. Think of this as the starting line. The point where the vector begins is called the initial point. If you're looking at a diagram, this is the tail of the arrow. So, if we have a vector that starts at point A, then point A is our initial point. Next, we have part B, the terminal point. This is the destination. The point where the vector ends is called the terminal point. In your diagrams, this is the head or the sharp tip of the arrow. If our vector travels from A and finishes at point B, then point B is the terminal point. Now, here is a very important tip for your notation. When you see the notation vector AB, written with an arrow over the letters A and B, that notation is explicitly telling you the direction of travel. It tells us the vector starts at A, which is our initial point, and ends at B, our terminal point. Now that we've established that a vector is defined by both magnitude and direction, let's look closer at how we actually draw and label one. This is what we call the anatomy of a vector. Keep this distinction in mind, because in the next slide, we're going to discuss how to measure the distance between these 2 points, which brings us to the concept of magnitude. 2. Understanding magnitude. While the initial and terminal points tell us where a vector is positioned and which way it is pointing, the magnitude tells us the size or the strength of that vector. Think of it as the how much part of the vector. To define this formally, the magnitude of a vector is simply the length of that directed line segment we just looked at, measured from the initial point to the terminal point. To make this more relatable, let's think about physics. If a vector represents displacement, meaning the movement from one place to another, then the magnitude is simply the total distance traveled between those 2 points. Now, let's look at how we write this down mathematically so you can recognize it in your textbooks. First, if we are using the notation for a vector from point A to point B, which we write as a vector B, we represent its magnitude by placing the notation between 2 vertical bars. So, you would say, the magnitude of a vector B is equal to the magnitude of a vector B, enclosed in vertical bars. Second, if we are using a simpler lowercase letter to represent a vector, such as a vector, we use the same vertical bar notation. You would pronounce this as the magnitude of a vector is equal to the magnitude of a vector, enclosed in vertical bars. Finally, it is worth noting that in some more advanced mathematical contexts, you might see the magnitude represented simply by the scalar letter, A, without the vector arrow. Now that we have identified the anatomy of the vector, specifically the starting and ending points we discussed in the previous slide, we need to talk about the third essential component, the magnitude. As we move to the next slide, we will discuss a very important rule regarding this magnitude, specifically, why it can never be a negative value. 3. The property of non-negativity. Now that we understand how to identify the points and the notation for magnitude, let's discuss a fundamental rule that you must always keep in mind. In vector algebra, there is a critical rule. The magnitude of a vector can never be a negative number. To understand why, think back to what we just discussed regarding the definition of magnitude. Since magnitude represents a physical distance, specifically, the length of that line segment between our initial and terminal points, And we know from basic geometry that distance can only be 0 or a positive value. The same logic applies here. Mathematically, we express this as the magnitude of a vector, written as the absolute value of is greater than or equal to 0. Because of this, if you ever encounter a mathematical expression suggesting that the magnitude of is less than 0, you can immediately recognize that it is logically incorrect and mathematically meaningless. It simply cannot happen in our coordinate system. However, there is one special case to note. If the magnitude is exactly 0, it means the initial point and the terminal point are in the exact same location. In this specific instance, we call this a null vector, or more commonly, a zero vector. Now, let's see how this concept of magnitude and direction works in a practical, real-world scenario. Real-world example: displacement of a vehicle. Now that we have covered the theoretical definitions of the initial point, terminal point, and magnitude, let's put all these concepts into practice with a real-world scenario. Imagine a car traveling in a straight line from city A to city B. We can use this journey to break down the anatomy of a vector step by step. First, let's look at step 1, identifying the initial point. Since the car begins its journey at city A serves as our starting position. In vector terms, this means city A is our initial point, or what we previously called the tail of the arrow. Moving to step 2, we identify the terminal point. The journey concludes when the car reaches city B because this is where the movement ends. City B is our terminal point, or the head of the arrow. In step 3, we can now represent this entire displacement using vector notation. Since the movement starts at A and ends at B, we write this as the vector A with an arrow pointing from A to B. This notation explicitly tells anyone looking at it exactly which direction the car traveled. Finally, let's look at step 4, determining the magnitude. If the physical distance between city A and city B is 50 kilometers, then the magnitude of our displacement vector, which we write as the magnitude of vector AB, using those vertical bars we discussed earlier, is simply 50 kilometers. One very important thing to note here, which connects back to our rule about non-negativity. Even if the car were to drive in the opposite direction, from city B back to city A, the magnitude of vector BA would still be 50 kilometers. As we learned in the previous slide, distance and magnitude can never be negative. Now, before we wrap up, let's look at some common pitfalls students encounter when working with these components. Common mistakes to avoid. First, be very careful not to confuse the vector itself with its magnitude. It is a very common error to use a vector and the magnitude of a vector interchangeably. You must remember the distinction we discussed earlier. A vector is the complete package. It contains both the direction and the magnitude. On the other hand, the magnitude of a vector written as the magnitude of a vector with those vertical bars, is just a scalar. It only tells you the size or the length, nothing more. Second, avoid the temptation to assign negative values to a magnitude. Sometimes, students try to put a negative sign in front of the magnitude to indicate that the vector is pointing in the opposite direction. Don't do this. As we learned in the previous slide, magnitude represents a physical distance, and distance can never be negative. If you want to show a change in direction, that is handled by the arrow itself or the vector's components, not by the magnitude. Remember, the magnitude of a vector must always be greater than or equal to 0. Finally, watch out for reversing your points. It is crucial to remember that the vector from A to B is not the same thing as the vector from B to A. While it is true that they share the exact same magnitude, their anatomy is different. In the first case, A is your initial point. In the second, B is your initial point. Because their starting and ending points are swapped, they are pointing in completely opposite directions. Now, before we wrap up today's lesson with our final summary, I want to pause and highlight some common pitfalls. I've seen many students stumble on these specific points during exams, so please pay close attention. Keep these distinctions in mind, and you'll avoid the most frequent mistakes in vector algebra. Key takeaways. First, remember the initial point. This is simply the starting point of your vector, which you can visualize as the tail of the arrow. Next, we have the terminal point. This is the endpoint, or the head of the arrow, where the vector finishes its direction. Third, let's talk about magnitude. As we discussed when looking at the car traveling between cities, the magnitude represents the length or the size of the vector. When you are writing this down, you can denote it using the notation absolute value of a vector, A, or, if you are using specific points, the absolute value of vector AB. Finally, and this is a crucial rule to keep in mind for your future algebra work, remember the property of non-negativity. The magnitude is always a non-negative scalar. In mathematical terms, we express this as the absolute value of vector is greater than or equal to 0. This means you will never encounter a negative value when calculating length or distance. All right, we have reached the end of our lesson. Before you move on to your practice problems, let's quickly recap the key takeaways from today's session on the anatomy of a vector to ensure everything is clear. If you have mastered these 4 points, you have a solid foundation for working with vectors. Great job today.